This is the presentation of the SCITC 2020 conference paper titled Anisotropic Diffusion and Decision-Based Sky Region-Aware Single Image De-Hazing for Surveillance. So starting with the introduction, the light scattering and absorption effects due to suspended particles in the atmosphere or in aquatic medium leads to hazy or foggy nature of images captured from weather-degraded scenes. Such distortions make it difficult for optimal operation of computer vision systems in applications such as intelligent transport and surveillance systems. Thus, single image de-hazing is a means of extracting the desired haze-free image seen, and this is an ongoing and ever-expanding area of research. Several algorithms exist in the literature and can be currently classified under four main categories, namely restoration, enhancement, fusion-based, and machine or deep learning-based methods. Those several algorithms already exist. They still suffer from problems such as halo effect, color distortion, edge and sky region over-enhancement, and image darkening. And some algorithms have also been proposed to solve some of these problems. However, they have varying degrees of success. Thus, our motivation for this work is to resolve the issues of the methods from the literature which yield inconsistent results. These alternative solutions from the literature also are mostly impractical and unfeasible and also highly computationally complex, and that makes it quite difficult to deploy on real-time embedded systems or computers with limited resources. In this proposed work, the main objective is to minimize over-enhancement of sky regions or avoid enhancement entirely of sky regions for images with thick haze and large sky regions. The proposed approach involves a series of schemes which include partial differential equations in a decision-based framework coupled with fusion and fast adaptive morphological processing. These all help to improve sky region discrimination and as a result avoid sky region over enhancement. So what image fusion? Image fusion combines the desired features of enhancement and restoration algorithms in addition to other processes to yield an enhanced output image. It can also be combined with machine or deep learning based approaches as required. There are numerous fusion algorithms for high dynamic range processing, including multi-focus or multi-exposure based fusion techniques. After several experiments, we selected a fusion algorithm proposed by previous researchers and combined it with decision-based, partial differential equation-based formulation to improve enhancement results while avoiding complexity. So in figure 1 we have the proposed approach. The input color hazy image is converted from the RGB color space to the HSI color space. Then we perform the inversion of that intensity channel of the image and compute the statistical parameters which are used in computation of the damped clip limit, which is CD. Then based on the decision box, this determines if the image has a sky region or not, and if it has a sky region, we compute the segmented sky region following the decision that goes with no label. So we compute the binary threshold on the thresholded image and then perform the morphological processing. Then obtain the sky region segmented image and use that in combination with the image to process it to eliminate over enhancement of the sky regions. But if the image has no sky region, which is indicated by the yes decision, then we perform the multi-scale, global, and local enhancement of that image, computing the logarithm and the single scale illumination estimation, the reflectance extraction via the difference of channels, then performing the gain offset correction. Then we fuse the two processed channels using the principal component analysis and isotropic diffusion based fusion method used by previous authors. And then we perform the contrast limited adaptive histogram equalization enhancement and perform the iterative process that needed to refine the image until we produce the desired results, after which we invert the image once more and combine the hue, saturation, and intensity channels converted from HSI to RGB. So in figure 2, we present some preliminary experiments and analysis using a sample image. So in image A, we have the original hazy image with considerable amount of sky region, and in image B, we have the inverted log illumination channel of that image, and in C, we have the morphologically processed binary image showing the clearly segmented regions of sky and non-sky regions. Then in image D, we have the fused segmented output from C using the amplified log reflectance. And then in image E, we have the fused segmented output using the fused log illumination from B and the reflectance. And in image F, we have the output using a previously developed De-Hazing formulation as compared with the output using amplified log reflectance in image G. And also in image H, we have the fused log illumination plus reflectance. Now comparing images F, G, and H, we can see that H has the least amount of color distortion and clearer skies with little over enhancement of the sky region, maintaining a more natural white background than the blue background that's observed in image F, and it's much more clearer. The details can be seen in the background. So we perform extensive experiments comparing the proposed approach with several algorithms from the literature, and the test images used were obtained from standard and benchmark datasets used in several De-Hazing experiments and publications in the literature from various journals and publications. The algorithms tested include those by He et al., Dai and Tarrell, Sulami et al., Chen et al., Berman et al., Gao et al., Meng et al., Berman et al., Zhu et al., Ren et al., Kai et al., B. Li et al., and C. Li et al. And these are mostly deep learning methods and restoration-based approaches, which we will elaborate on their terminology in the next slide. So this is a glossary of terms of the various algorithms compared against the proposed approach, and that includes the adaptive multi-exposure fusion and the non-local De-Hazing and the partial differential equation fractional multi-scale illumination reflectance based contrast enhancement system and the boundary constraint contextual regularization and color attenuation prior based methods, then the multi-scale convolutional neural network and the gated fusion network based approaches, also the all-in-one De-Hazing network and the cascaded convolutional neural network. So sample results are shown in figure 5. which includes methods by Hare et al., Meng et al., Sulami et al., Chen et al., Kai et al., Berman et al., Gao et al., and the proposed approach. And we can see that the proposed approach has the clearest skies of all the processed images with sky regions. Then for the images with high amount of detail, the proposed approach also reveals more detail than several of the other approaches with minimal color distortion. And for the images with no sky regions, the colors are much more vivid and enhanced. The same can be said for the first image as well, with minimal color distortion. Unlike some where the sky regions or the non-detailed regions are quite faint and mostly not properly enhanced or distorted, as you can see in the fourth column. So this makes it quite suitable for surveillance operations using drones, which have to take pictures of cities or buildings or large gatherings of people. So in hazy conditions, being able to extract the details of the scenes and to get the features of the components of that scene, which might include people of interest or objects like cars, vehicles, buildings, etc. The component of the proposed approach enables the viewer or the user to adequately assess the situation on ground without having to be in contact with the subject or object being surveilled. So this is quite useful for intelligent transport systems and also for surveillance systems, especially for remote surveillance from great heights. So in conclusion, the decision-based PDE-based algorithm has shown quite good results, and that its outcomes are much more consistent and surpass the results of majority of algorithms from the literature. And future work would involve testing the proposed scheme on much larger set of images to really understand the limitations and the drawbacks, as well as the full strengths of the proposed approach and how to improve on them for certain outlier images. So these are some of the selected references. Thank you for your time. I hope you enjoyed the presentation. Any questions?